the final third function we have to write is deleting a key, a word from our translation dictionary. So if we delete a word, we have to remove the node from the tree. Okay, let me start writing the delete function. Delete kt. We do again a pattern matching using the recursive structure of the tree. If t is a leaf, then of course it's already gone, so we just return a leaf. Otherwise, we have a tree with a key x value v, left subtree t1 and right subtree t2. We again use the and then to say where we are, if we're at the node or if we have to go left or right. So again, I do like this. So x equal k, x less than k, x greater than k. Okay, now let's fill in the blanks. If x is equal to k, that means we're at the node we want to remove. So one possibility is to replace this node by leaf. If x is less than k, that means k is greater than x. That means we have to go to the right subtree, and we do a similar approach like for insertion. We have to build a new tree with the node deleted that is not there anymore. So we return tree, key x, value v, and we're going to the right. So the leftmost tree is the same, and the right tree has the recursive call to delete. There we go. And the final case, I forgot a parenthesis, there we go. The final case, when x greater than k, that means k is less than x, that means k is in the leftmost subtree. So we go to the left, the node here stays the same, the left one is deleted, okay, kt1, and the right one stays the same, okay? So here's our function delete. So what do you think about this function? Is it correct? Think about it for a few seconds. Actually, this function is wrong. And in fact, delete is much harder to do than either insert or lookup. What's the problem? Well, assuming that x is equal to k, assume here we have a big tree and k is equal to x. We have to remove the root node here, but we don't want to remove t1 and t2, but if we replace by leaf, that's exactly what we're doing. So this solution is wrong. So what we have to do in this case, in the first case when x is equal to k, is remove the root node, but somehow keep the nodes in t1 and t2, and somehow put another node in the place of the root node. We have to keep the structure of an ordered binary tree. So here, bringing in the diagram, let me explain the situation. So here we have a tree, okay, with nodes a and x, subtrees, and so on, assuming that we want to remove x. So x disappears. Well, the resulting tree here, it's not an ordered binary tree. There's nothing there. So, in fact, we have to repair the tree after the x disappears. So how do we do that? Well, let's take a look at one case. Let's say when one of the subtrees is empty. Here we have no right subtree or no left subtree. In that case, it's pretty easy. If we delete x, we just replace this whole tree by the left subtree. And in the other case, when we delete x, we replace this whole tree by the right subtree, and we're done. But that's the easy case. What about the hard case? What about the case when both subtrees are not empty? Well, here we have that case, x with two subtrees. Let's say we remove x now. The node here in the root is empty. We still have the two subtrees. We have to somehow repair it. Here we have a hole. We have to put a node there. But which node do we put? Well, the node that we put there has to have a key greater than all the keys of the left subtree and less than all the keys of the right subtree. So what we could do is we could take the smallest element in the right subtree, let's call it y, and put it there. And the new right subtree then is the same as the old one without that smallest element. That's one thing we could do. If you think a little bit, you can see that there's another dual solution, but I'm not going to talk about the other solution. I'm going to do this one. I'm going to remove the smallest element from the rightmost subtree. Okay, let's do that. So here we go. This is the case that was giving us problems. The case when x and k are the same. Well, let's say we have a new function called remove smallest that does exactly what we want. It takes a tree and it returns a new tree, this one, for example, with without the smallest element, and it also returns the smallest element. So it returns a new subtree without the smallest element, and it returns the smallest element, the key and the value, as a triple. Okay, so remove smallest here of T2. We're going to remove the smallest element from the right subtree, and we return here. So TP here is the new right subtree without the smallest element, and YPXP is the smallest element. So then we can build this new tree in boldface here, which has Y as its node, a root node here, and which has T1 as a left subtree and TP as the right subtree. And it's done. There's also the case when T2 is empty. We can handle also that case by saying that remove smallest just returns none. There's no smallest element if T2 is a leaf, empty tree. And that's it. If we have this function, this magic function, remove smallest, we can solve the problem. Now, a small minor detail remains to solve. We have to define remove smallest. Okay, here's the definition of remove smallest. So remove smallest, of course, is a recursive function. It would also recurse down the tree structure, so we give it a tree T. If T is leaf, then none. This is clear. There's no elements in a leaf tree. If T is a non-leaf, a non-empty tree, then we can call remove smallest on its leftmost subtree, on T1, okay? Because the smallest node of this tree, T, is the same as the smallest node of T1, if T1 is non-empty, okay? Now we remove the smallest from T1. If T1 is non-empty, we get a triple here, and the result, the smallest element will be XP VP, which is the result from the remove smallest call, and we have to build our new tree, which is the same as the old one, but without the smallest element, so the only thing is the leftmost node is changed, okay? And we just have to handle now the case when T1 is empty. That's very easy. If T1 is empty, then the smallest here is going to be XV, as we saw before, and the new tree is T2, so we just return that. So this defines remove smallest. This may seem a fairly intricate function. It is a fairly complicated one. To really understand, to have a gut feeling, an intuitive understanding of what this function does, I recommend that you draw diagrams. Okay? Well, now we have these functions. Now let's fix the definitions here. Okay? So let's fix the definition of it. So what I have to do in this case, this is the only case where we were wrong, in fact, when x is equal to k, is I have to define remove small, I have to call remove smallest. Remove smallest T2 of none, then if T2 is empty, then I am going to remove XV. If T2 is empty, the result is going to be T1. Otherwise, I return this triple TP YP VP, and I have to return a new tree here whose key is YP value VP. This is the Y that we put in the hole. The left subtree is the same as before, and the right subtree is TP. Okay, that seems to be it. Okay, all we have to do now is define remove smallest. Let me do that here. smooth smallest t, case t of leaf, then none. That's clear. Otherwise, I have a tree here. Key x value v, a left subtree t1, right subtree t2. Okay, and now I have to get the smallest element of this tree. So I call remove smallest on t1 because that's the possible thing that might give a different result. If t1 is empty, this returns none. I then get triple of, if t1 is empty, the smallest is xv, the new tree is t2, like this. Otherwise, I have a triple here that I've returned. This one will give me the smallest, which is xpvp, the smallest element in t1. The new tree is tp. And then I have to return a triple, of course, with a tree. This tree has x and v as its value, the same as before. The left subtree has changed, it's tp, and the right subtree is the same as before. And the smallest element is xpvp. Okay, that's it. If I didn't make any mistakes, let me define this, feed it to the system. Variable R2 not introduced. This has to be T2. Let me define it now. Fine. Let me now define delete. Fine. And now let me see if it works. Let me browse T. Remember the tree we had in the beginning? Let me now remove an element from this. Which element should we remove? Let's remove a hard one. Let's remove the root horse from T. And what are we going to see now? What do you think? Did you know that monkey was going to be the new root?